For a particle in one-dimensional rectangular well, must there be at least one bound state? So the question is whether um, the number of bound states is greater than or equal to one. Should you have at least one bound state? Before I answer this directly, let's actually assume that it's not a requirement. Let's say that the number of bound states can be zero. Now, we're going to assume that and see what happens, like where this assumption leads us. So the number of bound states, if you remember, is given by this formula, right? B over pi less than or equal to n. So this implies that the constant b over pi is less than or equals n. If we are assuming n equals 0, this should be either 0 or negative, right? Now let's write down what exactly is b. B is this, right? And b over pi would be, I'm just going to write h bar as h over 2 pi. So we have b over pi to be, yeah, I'm just going to bring in this here. Oh, I believe I worked out all this. Yes, and the pi gets canceled. So yeah, there we go. So this is the value of b. Now let's see. This is a positive quantity. This is a positive quantity. The mass is positive. Potential is positive. So you're basically telling that b over pi is a positive quantity, right? So we know from the value of b that b over pi has to be greater than 0. It has to be greater than 0. But if you're telling that if you're assuming that the number of bound states can be equal to 0, you're saying that b over pi is either negative or equal to 0, right? And this leads to a contradiction. That doesn't make any sense at all. And that is because our assumption that the number of bound states can be 0 is incorrect. So n equals 0 is not an option. A particle in a rectangular well must have at least one bound state. At least one. So n has to be greater than or equal to 1. Now let's move on to part B of this question. This question is asking if the wave function is as continuous at x equals 0. Now, what is the value of this? What is it? So let's actually write it down. Okay, if you're wondering where I got this equation from, this is on page 29. It's part of the paragraph following equation 2.32. So you'll find this there. So the second derivative of your wave function is given by this. And we see that the second derivative is a function of your potential, right? And we know that V is discontinuous at x equals 0. So V, as x approaches 0 from the left side, let me just do it in an easier way. So, okay, the potential is equal to V0 when x is less than 0, right? But the potential is equal to 0 when 0 is less than or equal to x is less than or equal to L. So at 0, at x equals 0, your potential is 0. But when x is less than 0, your potential is V0. So clearly your potential is discontinuous at x equals 0. And that means the second derivative of the wave function, which also has the potential term in it, is also going to be discontinuous at x equals 0. So the answer for the question is psi is the second derivative of psi continuous at 0 at x equals 0. The answer is no. No, it's not.